Hey everyone, this is Derek, and in this video we're going to look at defining the derivative and look at a little bit of derivative notation as well. Okay, so where to start on all this? So in the previous section we had started with slope and we kind of went to average rate of change from there and then to instantaneous rate of change. And this progression is kind of what gets us to calculus, is that we're doing something where we're looking at an average rate of change like this red line. And then remember, we would let our h up here in our difference quotient go to 0. So we're letting this get closer and closer and closer until that approached what we called a tangent line. So that was our secant line and our tangent line. And so as I move this closer, right, this would just get to be better and better approximations of that black line. And we did that in the last section using this definition. I'm going to do that one more time and then we'll be into derivatives for real. But just to kind of show what the derivative is, again, the two things we've seen. One, it's the slope of the tangent line. So it'd be the slope of this black line right here at this point, whatever point that is. Two, it's also the instantaneous rate of change with respect to x at this moment. Okay, so from there, let's look at some notation for the derivative. Here's the one that I showed you in the beginning is f prime of x. And this one's pretty common. We use this a lot. Y prime is also pretty common. So if I'm given a function f of x equals some stuff, we're going to write its derivative as this f prime. If I'm given a derivative or a function as, y equals 2x or something, we're going to write that as y prime when we do the derivative. Dy dx, this is another way of saying the derivative of y with respect to x. So if I have a function, say y equals, 3x squared, I can take the derivative of both sides, saying dx to both sides. And so you're using it almost like an operator. And then you get this dy dx. What this dy dx is delta y over delta x when we're doing intervals, and that's our change in y, change in x. And so this is like our slope. So dy dx is like our slope, but infinitely small changes in x and y. Df dx, same idea. It's just when we're calling it the function f, and same thing here. This side, this is going to be notation for indicating the value of a derivative at a given point. So say I want to find the derivative and then evaluate it at 7. I would say f prime of 7. So it's the same as if I wanted to evaluate the original function at 7, I'd say f of 7. Now we're just saying f prime of 7. When we use these other notations down here, we have this kind of funky, I'm going to write this a little bit bigger, in this case like y prime with the line, and then evaluated at x equals a. And that's what all these ones are showing. So dy dx, same thing, the derivative evaluated at a given value. So there's some notation. And then we're going to do our last example using the difference quotient and slope, and just kind of use that to get us to this thing called the power rule that's going to make everything so much easier in just one more video. Okay, so this question is asking me to find the derivative, dy dx. It's finding the derivative using the limit definition. And again, this was my limit definition right here. And we saw that, like I said, back in the last chapter. So this is going to go it's going to go y prime equals the limit as h goes to 0 of, and this will be x plus h quantity squared minus x squared over h. So remember, we're doing, bring this back for a sec, f of x plus h, so x plus h is going in for x squared minus the function x squared and over h. And then, and I could have also written this dy dx, same thing from here. So the limit as h goes to 0, if I write these side by side in FOIL, remember, we're going to get x squared plus 2xh, careful not to lose the 2xh, plus h squared, and then minus x squared all over h. And then these cancel. And then remember that h divides in. So dy dx is going to equal the limit as h goes to 0 of 2x with h there, and then plus h. So then letting h go to 0 knocks out this term. So then I have dy dx equals 2x. So what that means is if I take the derivative of x squared, its derivative is 2x. Okay, so what does that mean? That means, so remember the derivative is, let me go back to, where'd it go? Here we go. The derivative is the slope of the tangent line at that point on a curve or line. It's also the instantaneous rate of change. So what this is an equation for the slope of every single point on this curve. And then I'm going to show you what that looks like as the next part of the example. Okay, so from the last page, there's our original function, which is this parabola right here, x squared, and then we found our derivative is 2x. So, and what I'm saying is that here we have this curve, and if I found the slope at every single point on this curve and then graphed it, what it would be is 2x. So this is the equation for every one of the slope, every single slope at every point on that curve. So part B is asking me to find the instantaneous rate of change of the function when x equals 1. Okay, so if I wanted to be a little fancy, I could write that as dy dx evaluated at x equals 1. So I'm evaluating the derivative at x equals 1. So that's a lot of writing to just say 2 times 1, but if we're being all proper, then 2 times 1, and that makes 2. So find the instantaneous rate of change of the function when x is 1. So what I found is that the instantaneous rate of change is 2. And so if I come over here to my graph and just kind of show what that looks like, here we are at x equals 1. And if you look at, I drew a tangent on here. So I'm just touching this point, this graph, this one point at x equals 1. So the slope of this tangent line should be the same thing as the instantaneous rate of change, because that's what this finds, is that slope. And if you look, we are going, it goes up 2, right? And then it goes right 1. And so rise over run, there's 2 over 1, there's my slope of 2. So this m right here equals 2, and that's what this is saying. So at 1, my slope will be 2. And then find the slope of the tangent line at x equals -2. So this is the same thing as the instantaneous rate of change. Slope of the tangent line, instantaneous rate of change, same deal. So now we're just plugging in -2. So dy dx evaluated at -2 will just be 2 times -2 or -4. So the slope when x is -2 at that point should be -4. And here, if you look, we're going to drop 4, and we're going to run 1. So that's our -4 over 1, or -4. And then the last question here is, where does the slope of the tangent line equal 0? We're going to spend some time looking for where the slope of the tangent line equals 0, because that's going to be the turning points of the graph. That's where something is either bottoming out or where something is at like a max. So that will be our maximums and mins, and that's how we're going to find those. So the slope of the tangent line comes from the derivative. So since I have the equation of the derivative, I can just say, where does the derivative equal 0? So anytime you see this, this is the same thing as saying dy dx, make that 0, or f prime of x, make that 0, whatever notation we happen to be using. And I divide the 2 over and I get x equals 0. So that actually makes complete sense, because if you look right here on the vertex, if I drew a tangent line to that, what's the slope? 0, right? Because that's where it's flat. So the places where the tangent line equals 0 is what's going to be called these turning points. Okay, so the last thing for this video is conditions for non-differentiability. So this is the things that would cause a function to not be differentiable at some given point. And there are 3 of them. So for the first condition is f is not continuous at x equals a. So if the point doesn't actually exist, I can't take the derivative there, because I wouldn't be able to draw a tangent line to something that isn't actually there. So it has to be continuous. If we're going to find the derivative at a given point, it's got to be there. The second thing is that if it has a corner, like absolute value x, then there isn't a unique tangent line, because how do you draw a tangent to a corner? When you're coming up this side, it's going this way, and then some weird like flip happens and now it's over here. So corners are not differentiable. And then likewise, if it has a vertical tangent at x equals a, you can't differentiate that either. So here where we have a vertical tangent or a vertical tangent. Okay, so then for this last example, we're supposed to find at which integers the function shown is not differentiable. And so we have kind of all these points on this graph. So -1 look good. 0, that one would be bad because it looks like there's a cusp. 1 wouldn't work out because it's a hole, it's not there, so that's the first one. 2 looks fine. 3 looks like an asymptote, a vertical asymptote going on, so that's not going to work out. 4 is the other spot, so there's this gap, so I can't differentiate over a gap. So those would be the 4 spots where I would not be able to differentiate that function.